All right, hi folks, this is Larry Mussolino. I'm recording a video for Section 3.4, and this section looks at applications of the derivative mostly in economics. So in the business field, derivative is used very frequently to analyze economic scenarios. Here's a summary slide that'll be useful to list out some of the terminology we'll be using. All right, first, in this, go to the very bottom of the slide. Notice here it says we use X to represent the number of units being sold, and P is the price per unit. So the revenue function is just P times X, right? Imagine selling, a certain number of, let's say, motorcycles at a certain price. Multiplying those two numbers gives you the revenue. Profit is taking revenue minus cost. Anytime you're interested in marginal functions, and we'll be talking more about this in a few minutes, but a marginal function really means take the derivative. So if you wanted to know what is the marginal cost function, you take the derivative of the cost function. The marginal revenue function, notice we're going to notate these with a apostrophe. P prime of X would mean the marginal profit function. There's also an average function where you take the function and divide by X. Well, that kind of makes sense. When you're taking the average of a set of numbers, you divide by how many numbers you started with. So here, let's say we wanted to know the average cost function. We'll label that as C bar. Just take the cost function, divide by X. We can also calculate what's called the marginal average function. And again, that just means the derivative of the average cost function. Also, we'll be talking about something called elasticity of demand. That's going to be this E of P function. Notice it's going to involve a derivative, and we'll talk more about that in a little bit. All right, so what is marginal cost? Marginal cost is the actual cost for producing an additional unit of a certain item. So we're going to be able to calculate this marginal cost as a derivative function. All right, let's do an example here. So here it says the total weekly cost is given by this function. So here's C of X, it's the cost function. And it says what is the actual cost if you want to produce the 1031st unit and the 2161st unit. Well, this C of X function is the cost to produce a total number of units. So if I want to actually figure out the cost for the 1031st unit, the way I could do that is, let me make a little note here. If I want to calculate this cost, what I could do is find C of 1031. That's really the cost to produce all 1031 units. And let me subtract the cost to manufacture 1030 units. Well, if I take these two costs and subtract them, that must give me then the cost to manufacture only the 1031st unit. So remember, the C of X function is really giving you the cost to manufacture the total number of units. For example, if I was to ask you to calculate C of 1,000, that would be the cost to manufacture 1,000 units. But here, this question, they're really asking me to calculate one unit. It happens to be the 1031st unit. So you'll use this method that I'm circling here in the red box. And of course, you know how to calculate C of 1031. Just go to this original C of X function and replace X with the number 1031, and then work that out on a calculator. Now it's asking, what is the marginal cost when X equals 1030? Marginal cost means take the derivative. So take C of X and take its derivative. That'll give you C prime of X. And then they're asking you to calculate C prime of 1030. That means you'll go to the C prime function and replace X with 1030. What you're going to see is these two answers are going to be the same. Notice they both happen to be $1.79. What they're trying to show you in this example is if you take the derivative and evaluate that at x equal 1030, that's really the marginal cost. So it's really the cost to manufacture the 1031st disk, and you'll confirm that by kind of working this out as a subtraction also. So again, marginal cost means the derivative function. How about average cost? Well, average cost you figure out by taking the total cost and dividing by the number of units produced. So the way we would write this C bar function is this fraction you see here. Take the cost and divide by x. We could calculate the derivative of that function. That would give us the marginal average cost function. Again, anytime you take the derivative of these economic functions, you're generating a marginal function. So a quick example. Here is a cost function. You might remember this 400 represents the fixed cost. This 20 represents the variable cost. It says find the average cost function and then find the marginal average cost function. All right, let's find the average cost function first. Remember, you take the cost function, divide by x. So here it is. I can simplify this a little bit because what I could do here is break this up into two separate fractions. So I'll take the 400 and put it over the denominator x. Then I'll also take the 20x and put it over x as well. Of course, 20x over x, these x's cancel out, and I'm left with this result. Now they want me to take the derivative of this function. Well, before I take the derivative, let me write it like this: 20 plus 400 times x to the minus 1. Remember, x in the denominator can be rewritten as x to the negative 1. Let me take the derivative. Well, the derivative of 20 is just 0. Remember, the derivative of a constant is 0. Let me take the derivative of 400x to the negative 1. Well, the derivative is going to be to bring down that 400 because that's just a constant in front. Bring the exponent negative 1 down as a multiplier and then subtract 1 from the exponent. So that gives me x to the negative 2. Now I can bring that x to the negative 2 down to the denominator and write it as negative 400 over x squared. Okay, you'll be doing a few of these examples also in WebAssign. All right, here's another question. What's the limit as x goes to infinity for this average cost function? So as you make more and more units, right, x is getting larger and larger, what is your cost going to approach in the limit? It's almost like asking you, how low can you get your costs for this business? Well, if you take the limit as x goes to infinity, you might remember when x is in the denominator, right, 400 over a very large number goes to 0. So the limit as x goes to infinity, the answer here is 20. So as the production levels increase, the costs will go down, but they're going to approach this kind of this horizontal asymptote of 20, and you can see that clearly in this diagram. This is the cost function, but notice as x is getting bigger and bigger, the costs are getting closer and closer to this horizontal asymptote of 20. And that's the same conclusion we came to by looking at that limit. All right. So here's an example in WebAssign similar to what we just did. Okay, so first question, of course, they're giving me a cost function here to begin with, and they want to know what's the average cost function. Well, remember, the average cost function is take the cost function, divide by x. Then they want me to find the marginal average cost function. Well, for the marginal average cost function, you take the derivative of the answer you got in part A. And remember, for the answer you got in part A, you'll want to take this x and move it upstairs and rewrite it as x to the negative 1. And now they're asking what happens to the average cost function when x gets very, very large. Well, if x is getting very, very large, then this fraction is going to go to 0. And so you can see the answer is just 101. All right, how about revenue functions? Remember, revenue is how much money your business is taking in. If you think about P as the price for whatever you're selling and X is the number of units you sell, it makes sense that the revenue is just the price times the number of units. Okay. However, it says here the price can be a function of what's happening in the market. So remember, there's that kind of market equilibrium going on that we talked about earlier, where supply and demand kind of interact. All right, well, we come up with this demand function, and when we go ahead and calculate the revenue, it's really going to be a function of X. So this demand function, I'm trying to tell you, is going to depend on X, the number of units. So we're going to see the revenue function is going to be a function of X. Marginal revenue is going to be the derivative function. It's the revenue that you obtain from selling one additional unit. So when we calculate R prime of X, that's going to be the marginal revenue function. Remember, derivative measures the rate of change. So R prime is really telling you the rate of change of the revenue function. All right, let's do an example here. So this is the price for some loudspeakers. So it says the price is negative 0.02x plus 400. What this function is trying to tell you is the price depends on how many units you sell. And that probably makes sense. You probably know from your own experience that the price depends on the number of units sold. It says find the revenue function, find the marginal revenue function, and then calculate R prime of 2000. All right, well, the revenue function is P times X. But remember, in this example, P was given as this function, so this is P. So multiplying P times X, and I end up with this quadratic function. So this is R of X. Now they want the marginal revenue function, that's R prime, so I'm just going to take the derivative of R of X. Then they want me to calculate R prime of 2000. Really what that's saying is what's the marginal revenue when I'm selling 2000 units? Well, if you replace X with 2000, you end up with the answer 320. So when you go to sell the 2000 first loudspeaker, you're going to get an additional revenue of $320. Okay, let's go to a WebAssign example. So here they're giving me a revenue function. They want to know what is R prime of X. So for that, I'm just going to take the derivative function. Here it is. Then they want me to calculate R prime of 19. Well, that's just asking you to go to the R prime function and replace X with 19. Work that out on your calculator. Now, when you think about this, what's happening is the derivative function, this revenue function is quadratic. You might notice the coefficient in front of x squared is negative. Well, that tells me the graph of this is a parabola. Well, here it happens that R prime of 20 equals 0. Well, remember the derivative is the slope of the tangent line. So if the derivative at x equals 20 happens to be 0, that must mean the slope of the tangent line must be horizontal. Remember, when you have a slope of 0, it means you have a horizontal line. So this is m equals 0, and this happens at 20. I know that because when I took the derivative at 20, I got the answer 0. And the derivative is the slope of the tangent line. So it says here, what price should the airline charge in order to maximize revenue? Well, the maximum revenue is when this derivative is equal to 0, and so it makes sense I should go with $20 as the price to maximize the revenue. All right, how about profit? So profit is going to be the revenue function minus the cost function. The marginal profit function, P prime, is the rate of change of the profit. Profit you get from selling one additional unit of whatever is your manufacturing. All right, so here is a cost function for that loudspeaker. You might remember we already had the revenue function in the previous example. And they want us to find the profit function and then the marginal profit function and then calculate P prime of 2000. All right, well, remember here was the revenue function from that earlier slide. So to calculate profit, you just take revenue minus cost. So here's the revenue function. Circle it in blue. Subtract the cost function. I'll circle it in red. The only thing you have to be careful about is this subtraction is going to apply inside the parenthesis and change the sign of every quantity in that second parenthesis. So when you do that algebra and combine like terms, you get this profit function shown here at the very bottom of the slide. So that's the profit function, but then they wanted also the marginal profit function. So this marginal profit function is just coming from the derivative of P of x. Let me go back to P of x for a second. You'll take the derivative of this function. By the way, remember when you take the derivative of a constant like $200,000, that derivative is 0. So this is the derivative function. And they wanted us to come up with P prime of 2000. So I'm going to replace x here with 2000. And I get the answer 220. So the actual profit I get from selling the 2001st loudspeaker is $220. Here's what the profit function looks like. And you can see, very often, of course, a business wants to be able to maximize profit. So a business is interested in operating here at the peak of this curve. And remember, at the peak of this curve, the derivative P prime is equal to 0. So we often use this derivative function set equals to 0 to design the optimal units to maximize profits. All right, let's look at a WebAssign example. Here's a cost function. Here's a revenue function. They want us to figure out the profit function. For that, I'm just going to take the revenue function, that's this guy, and subtract the cost function. Right, so profit is revenue minus cost. When you work out the algebra there, you should get this answer in the green box. Now they want me to figure out the marginal profit function, P prime. So now you take the derivative. Again, remember, when you take the derivative of this 33,000, derivative of a constant is 0. Then the last part just says, what is P prime of these specific x values? So for P prime of 3100, I'll just go ahead and take the P prime function and replace x with 3100. So that'll be negative 0.08 times 3100 plus 690. You work this out on your calculator, and that'll get you marginal profit. All right, well, one more item to discuss. There's something called, in economics, what's called elasticity of demand. And this involves a derivative function. So what we're going to end up doing is thinking about the change in the size of a quantity divided by the actual size. We call that relative change. You could probably relate this to like a percentage increase And so what we're going to end up doing is calculating the derivative of a function divided by the original function. Now, what we're going to do is take that demand function and write it in terms of x. So sometimes the demand function is given to you as p equals something, and the something, of course, involves x. But we're going to flip this around, and instead of solving for p, instead of having p by itself, we're going to do some algebra and get x by itself. So we're going to do a little algebra and get x all by itself on the left-hand side, and then p will be on the right-hand side. You might say, well, why do we want to do that? Well, the elasticity of demand formula involves f of p. So this function, x, that we're going to come up with is going to be the f of p function that we're going to need for that formula on elasticity of demand. We'll do an example in a minute to show you how this gets set up. All right. So, usually the quantity demanded decreases as a unit price increases. This makes sense. I think, if a manufacturer starts increasing, let's say, increasing the price of iPhones to $2,000, well, the demand is going to go down, right? At some point, iPhones are too expensive, and people don't want to buy it, so the demand goes down as price increases. So typically, a demand function will look like this kind of curve. All right, for elasticity of demand, here's what we're going to do. I'm going to jump to the slide. What we want to do is calculate this quantity that you see here in the gray box. So remember, the demand function we're going to be writing as x equals f of p. All that means is the demand function is going to be x equals something where x is by itself on the left-hand side. We're going to call this function f of p. We're also going to calculate the derivative, f prime of p. And then once we do that, we're going to plug into this formula. It says p times f prime of p divided by f of p. And notice there's a negative sign in front. All right, when we do these calculations, what you're going to see is we end up with a numeric value. So let's do a quick example here to see how to set up that elasticity of demand. All right, so here is the demand equation. P equals negative 0.02x plus 400. But what we're going to want to do is solve this equation for x to get started with this kind of analysis. All that means is do some algebra to get x by itself on one side of the equation. So let me do that. Let me subtract 400 from both sides. When I do that, I'm going to end up with p minus 400 equals negative 0.02x. Then I'll divide both sides by negative 0.02. When I do that, I'll show you the results on the next slide. We're going to end up with x equals a function. We're going to call this the f of p function then when we do that. We'll go to the next slide and show you that worked out. So here is x equal f of p. This was taking that demand function from the previous slide and solving for x, getting x by itself all the time. So this function is f of p. All right, we're also going to need the derivative. So let me take the derivative of this function, but the derivative of this function is just negative 50. Okay, now let's go ahead and plug into that elasticity of demand formula. Here's the formula. All right, f of p prime we just figured out was negative 50. F of P was this negative 50P plus 2,000. So I end up with this formula for E of P. And then what they asked me is, what's the elasticity when the price is 100? So I plug in 100 into this form. I replace P with 100, and I come up with this answer 1/3. So let me go to a slide that explains more about this elasticity function. When you get a result for that E of P that's greater than 1, we say the demand is elastic. If that E of P is less than 1, we say the demand is inelastic. And if E of P is exactly 1, we say the demand is unitary. Now, in the example we just did a minute ago, E of P turned out to be 1/3. Remember in the example we just did, E of 100 turned out to be 1/3. Well, 1/3 is less than 1. So that example, we would say the demand is inelastic. You might say, well, what does that mean if the demand is elastic or inelastic? Well, it says here, if the demand is elastic, then the change in revenue and the change in price move in opposite directions. So as you increase the unit price, if you increase the unit price, the change in revenue can decrease. If the demand is inelastic, they move in the same direction. So if you increase price, the change in revenue is going to increase also. Let me give you some examples of elasticity to make it a little easier to understand. Let's say we want to talk about elastic demand. Remember, that's when the elasticity function is greater than 1. So you increase the price by a certain percentage. What happens to the percentage change in demand? Well, as the demand decreases, the revenue is also going to decrease. This is an example when there's competition. But how about Heinz soup? Imagine Heinz soup increases their price. They expect the revenue to increase. Well, people can buy other soups. The same with a Nissan Altima. If Nissan increases their price by a certain percentage, people might turn and buy other types of cars. How about inelastic? This is as the demand, you increase the price by a certain percentage, then as demand increases, revenue increases. This demand is inelastic here. This is when there's not much change in demand. You can think of it that way. Think about the water bill for your house. If the price goes up, you're probably still going to use the same amount of water. If Apple raises their iPhone price slightly, people might still buy iPhones. Airline tickets at Thanksgiving. People want to fly at Thanksgiving. So that demand is really not that sensitive to price. All right, let's go do an example from WebAssign. So it says here, here's the demand equation, P equals 148 minus X squared. And they want to know, what is the elasticity when the price is 28? All right, let's work this through. First, we need to rewrite the demand equation by solving for X. This is a typo. I should say solving for X. So let's go ahead and do that. What I'm going to do is, let me take this equation and let's do a little algebra. To make this easy, I'm going to bring X squared over to the other side. So it's going to be X squared plus P equals 148. Let me subtract P from both sides. So X squared equals 148 minus P. Now I'm going to take the square root of both sides. So X is the square root I'm just going to write it as 148 minus p to the 1/2. Okay, this is the f of p function. Well, in this elasticity formula, we also need the derivative. So let me also work out the derivative function, f prime. Well, I'm going to need the chain rule here. I'm going to bring the 1/2 down in front as a multiplier. Keep the function inside the parenthesis. Subtract 1 from the exponent. And now I got to take the derivative of what's inside the parenthesis. Remember, the chain rule says you got to take the derivative of what's inside. But the derivative of what's inside is a -1. All right, now let's go ahead and calculate the elasticity. All right, so I need -p. Now let me write the derivative formula. That's going to be -1/2 148 minus p to the -1/2 over f of p. But f of p was 148 minus p to the 1/2. All right, let me do a little bit of algebra here. First, let me move this -1/2 expression down to the denominator. When I do that, the elasticity, let me try to write it here. The elasticity, now notice here I have a negative and another negative, so that's going to flip to be positive. So this is going to be p over 2. The 2 is coming from that 1/2. And now I have 148 minus p to the 1/2 times 148 minus p to the 1/2. This is kind of like the square root of 148 minus p times itself. Or you can think about it when you multiply the same bases, you add the exponents. 1/2 plus 1/2 is going to equal 1. So when all is said and done, E of p is going to be p over 2 times 148 minus p. This is the elasticity function. All right, the last step, they're asking me to evaluate this function when p is 28. Well, to do that, I'm just going to replace p with 28 in this function. I'm going to let you work it out. But if I replace p with 28, it's going to be 28 over 2 times 148 minus 28. And when you work that out on your calculator, you should get the answer 0.017. Because that value is less than 1, we call that inelastic. Remember, if this number had been greater than 1, we'd be calling the elasticity, we'd be calling it an elastic demand. But here, because E is less than 1, we say the demand is inelastic. Okay, hope this is helpful as you are working here in section 3.4 that deals with economic type functions.